Okay, so it is now 2. So the first speaker this afternoon is Curtis McMullen from Harvard University. It's my honor to introduce you, Kurt. So I have actually prepared a very long introduction for him, but he tells me he has prepared the slides for 1 hour and 10 minutes. So I'll skip my introduction. And title of his talk is Billiards and Arithmetic of the Non-Arithmetic Groups. So go ahead, Kurt.
Okay, thank you, He. Well, it's a real honor to be part of this conference. I want to say something that people maybe haven't mentioned yet about Peter, which is that in addition to being a master of mathematics from analysis to arithmetic, I urge you to attend to this. The next time you see him give a talk, he is also a master of mathematical rhetoric, including the subordinate clause, to truly capture the peaks and valleys of a landscape of ideas. Okay, so I've chosen a topic that has the word arithmetic in it, and I'm not going to give a historical account in the interest of time, so I'll just mention this, some of the ideas go all the way back to Day and Manin, Birch, then through work of Veach, and many people recently. That is indeed Frank Caligari at the end. But I want to start by turning to the first time I believe I met Peter. This was around 1983, and this is an excerpt from a paper he was writing then with Phillips. And you'll see there's a configuration of 2 lines and 2 circles here, really 4 lines, and then some numbers. The numbers go up to about 1 million, and then there's some other numbers being calculated here. And it was a tremendous encouragement to me this first time I met Peter, and in all the subsequent times I did, that he was working in areas of mathematics that were simultaneously very deep and at the same time made contact with concrete geometric and arithmetic objects. I was a student at Harvard at that time, and the real numbers were considered an analog of the p-adic numbers. So it turns out that these numbers that are being computed here are they're related to a long-time interest of Peter's, which he recently rekindled with his Chern lectures, around a very broad topic called base notes. This one in particular has to do with the base note or lowest eigenvalue of the Laplacian of a particular hyperbolic manifold. And the corresponding limit set is the famous Apollonian gasket. And these numbers are approximations to the Hausdorff dimension of this famous residual set here. Around the same time, I had developed a Markov partition eigenvalue algorithm to compute this dimension to somewhat higher accuracy. So I was very excited to see that somebody else was interested in this topic. And we both get 1.3. Oh. So this has to do with base notes, but there's another aspect to this picture which I want to remind you of, which is that this limit set is associated to an infinite volume hyperbolic manifold, which is an infinite sheeted covering space of the complement of the Whitehead link. And so there's really close connections between topology, hyperbolic geometry, eigenvalues of the Laplacian here. But for the purposes of our discussion today, maybe what's most important is that first, this limit set corresponds to a subgroup of infinite index in the fundamental group of this knot complement. It's obtained by just cutting one of these, cutting along the disk spanned by one of the components of the Whitehead link. Just cut it open and you get a submanifold with boundary, and it's the infinite index subgroup corresponding to that submanifold. And it's an example of a subgroup of SL2C, which is not a lattice, but which is Zariski dense. And in fact, it sits inside of an arithmetic group, SL2Z adjoin I. And this is an instance of a topic Peter and his many collaborators were to take up in great detail and very richly later the theory of thin groups and corresponding expansion phenomena. And what I'd like to discuss today is some connections between thin groups and arithmetic and the elementary theory of billiards and polygons. Okay, so here's the first topic related to billiards. So it will have to do with periodic trajectories. So let's do some experiments. So the first interesting billiard table after the regular foregone, the square, is the pentagon. So we know that a billiard trajectory in the square is periodic if and only if its slope is rational. But there's also lots of periodic trajectories for billiards in the regular pentagon. So this is actually a billiard path. It hits the sides and reflects in the usual way, classical mechanics. And it comes back to where it started. In fact, it's known that there's a dense set of slopes which give rise to periodic trajectories. Okay, so a very natural question is, which slopes give rise to periodic trajectories? And how do these periodic trajectories behave? For example, this one looks very evenly distributed. So let me show you the results of a computer experiment that you can easily carry out yourself. If you start with a slope that's parallel to one of the sides of the pentagon, say this side here, you get an inscribed star, and the combinatorial length of this closed trajectory is 5. But if you change the slope just a little, so let's say we multiply it by an integer, say 4, then the length of the trajectory becomes significantly longer. It doesn't multiply by 4, it multiplies by about 100. And if we multiply by 20, we get a trajectory that's so long that the picture looks essentially black. And if we capriciously multiply by this integer, which is not too big, we get a trajectory whose combinatorial length, the number of sides it hits, and also roughly its Euclidean length, is about 10 to the 25. So there's this very rapid growth in the lengths of these periodic trajectories. However, most of the slopes we try, if we take multiples of this initial slope s, end up being periodic, although it might take an enormous amount of time to verify the periodicity by a naive procedure. So here's the first theorem, and most of the results I'm going to discuss have analogs for some regular billiards and some other regular polygons. Some have analogs in all, and some have analogs going beyond that into the theory of Teichmuller curves. But for concreteness, I'm going to concentrate on the pentagon today. So the first theorem is that the slopes of periodic trajectories in the regular pentagon are everything they can be. So there's an elementary argument that the slope has to lie in the field q adjoint square root of 5 times the slope s. And q adjoint the square root of 5 occurs, of course, because it's the totally real subfield of the cyclotomic field, q adjoint a fifth root of unity. It's a quadratic field. But more interestingly, we can bound how long the trajectory with a given slope is in terms of the naive arithmetic height of this number x lying in the field q adjoint root 5. And the log of the length is bounded in terms of the height squared. And here the height, you can think of this as naively the height of an integer is just its logarithm. And what this means is that you could have a slope that's roughly described by the number 10 to the n, and the length of the trajectory might be like 10 to the n squared. And in fact, this exponent 2 is sharp. So this result tells us that we see periodicity everywhere that we possibly could, and it also gives a bound, an effective bound, on how long we have to wait to see this periodicity. Yes? Yeah, so the question was, does periodicity depend on where you start in the pentagon? So you'll notice that I capriciously chose my starting point to be an edge midpoint, and I will do that throughout the talk. It turns out that once it's periodic for one starting point, it's periodic for all. So we can talk unambiguously about periodic slopes. That's right, that's right. So you'll get sort of, in this case, you'll get a sort of double cover of the star if you move the initial point a little bit to the side. Anything else? Okay. This is what I love about billiards, is you can actually ask questions. Okay, so let me just say a word about how this how this theorem is proved and what it has to do with groups. So there's a beautiful theorem due to Bill Veach, which says that quite generally, the periodic slopes in a regular pentagon, and there's an analog for the regular n-gon, they correspond to the cusps of a certain triangle group, which I'll call delta 5, because it has to do with the pentagon sitting inside of SL2R. So the cusps are the fixed points of parabolic elements, and we'll see this geometrically in a moment. So here is what the renormalization group looks like. It's traditionally called the 2-5 infinity triangle group. So you'll notice this is a tiling of the upper half plane by fundamental domains for the group. You'll notice it looks a lot like the tiling for SL2Z, except there's a lot more fundamental domains coming together at this vertex. There's an element of order 5 in the group instead of order 3, as we would have for SL2Z. And this group somehow governs the behavior of all billiard slopes, periodic billiard slopes, and many other things in the regular pentagon. Now, what is the power of this renormalization group? I'm not going to unpackage where all this information comes from, but the power derives from the following idea. Although combinatorially, there's enormous complexity in the different slopes of periodic trajectories in the pentagon, there is a renormalization procedure that allows you to relate apparently unrelated trajectories. And it turns out there's only one type of periodic billiard up to the action of this group. And in fact, the types of periodic behavior correspond to the cusps of the quotient of the upper half plane by this group, which is the 2-5 infinity orbifold. It has exactly one cusp, like SL2Z. So there's a tremendous combinatorial simplification in the use of this renormalization group. On the other hand, it means that to understand the pentagon, we have to understand this particular subgroup of SL2R, this Fuchsian group. Now, here's where the thin groups come in. So there's this associated field Q adjoining root 5. Its ring of integers is generated by the golden mean over Z. And it turns out that this group, SL25, is closely related to the group SL2 of the ring of integers in this field. Now, the ring of integers, Z adjoin gamma, that's a dense subring of R. So the natural thing to do with that ring is not to embed it into R, but to embed it into two copies of R using the two real places of the field. And if you do that with the group, SL2OK, you get a lattice inside SL2R. In fact, this is an example, one of the prime examples of an arithmetic lattice. So here we see arithmeticity and finite covolume. And then the group of interest is of infinite index in this group, SL2OK. And it's what's called a thin group. And it's non-arithmetic, and it's Zariski dense if you were to project it into SL2 R squared. So that's roughly speaking the definition of a thin group. Is it's of infinite index, but it's Zariski dense. Okay, so this brings us into the circle of ideas of the thin groups, and it also brings us into the world of non-arithmetic groups. And what I want to remark on is just this general fact that non-arithmetic groups, whatever they are, they're mysterious. And let's concentrate on this one example. So if you like, it's generated almost by the same generators as SL2Z. You have this inversion, Z goes to -1 over Z, but then here you have translation by the golden mean rather than translation by 1. And here's, again, a picture of its action on the upper half plane. Here's the famous 2-5 infinity triangle. The reflection through the sides of this triangle gives a group that contains our arithmetic group with index 2. Now, why do I say they're mysterious? Well, one of the natural questions you can ask is, what numbers can occur as matrix entries in this group? And the answer is no one knows. I mean, you just take the generators and multiply and you get examples, but there's no characterization. Whereas in SL2Z, we know that every integer occurs. Moreover, in SL2Z, we know that if you have any two relatively prime integers, then they occur as a column of SL2Z that characterizes the columns. For this group, there's no known characterization of the columns of that type. And finally, we can ask where are the cusps? That is, these are these points that you see at the bottom of the picture. This triangle comes down and touches the real axis at the origin. There's many other places where it touches. So the first theorem answers one of these questions, the theorem about also being periodic, and it can be reformulated in terms of this non-arithmetic group. Namely, the cusps of delta 5 are as big as they can be. They coincide with the points on the projective line over the field Q adjoins square root of 5. And then there was this business about how long the trajectories are. That has something to do with the columns in this group. And I'll just say they satisfy quadratic height bounds, which is what you need to get the result, the geometric and dynamical result I mentioned earlier. So geometrically, you can build these cusps of this group in a fairly simple way. It's kind of similar to building the Apollonian packing or the fairy sequence. So what you do is you draw a straight line, say at height 1 in the upper half plane, and then you pack 4 adjacent circles underneath it. So if you consider the region above this straight line as a circle, you have 5 circles arrayed around this point here. And then between every pair of circles, you add 3 more. So you get a packing of the upper half plane, or partial packing by round disks that meet in collections of 5. And then the statement is that the points on which these disks rest comprise all of the points in the field Q adjoining root 5. And moreover, this can be made more constructive. So let me give you a little reformulation of what turns out to be essentially the same result in terms of continued fractions. These are what I call golden fractions. So you start with a number in Q adjoin root 5, and you expand it as a1 plus 1 over a2 plus, except you don't take a1, you take a1 times gamma, gamma being the golden mean. So you take your number and you try to write it as a multiple of the golden mean, get a close approximation as you can. Then you invert it and do the same thing over again. And the theorem is that every element of this field can be expanded as a finite golden fraction. So this process eventually terminates no matter what slope we start with. Okay, so that's for those of you who like algebra and don't like pictures. That's a billiard-free way of discussing the main theorem. And then the height bounds correspond to the fact that in terms of the height of this slope, you can estimate how long it will take for this algorithm to terminate, and you can estimate the size of the integers a sub I that occur in the continued fraction. Another way to say this, closely related, is that every element of this field can be written as what I call a golden fraction, a ratio of 2 integers in the field, unique up to sign. And you might say, well, but that's obvious. Every element of the field can be written as a ratio of 2 integers. But the important thing here is that, in general, once you've written a number as a quotient of 2 integers, you can multiply the top and bottom by a unit in the field. For example, gamma itself is a unit in the field. So in general, this would be ambiguous up to multiplying the numerator and denominator by a power of the golden mean. But if we require that these 2 numbers a and c form a column in our matrix, then in fact this expression of x as a golden fraction is essentially unique. And then the height bounds say that the height of a and c can be bounded in terms of the height of x. But again, it's a quadratic bound. These numbers a and c might be much larger than the simplest description of x. Okay. Now, I want to give a glimpse of the complex geometry underlying this discussion. And I just, for a moment, open the hood and look at the details of the proof, because it makes contact with many topics that have been already discussed in this conference. So the first thing is that the quotient of the upper half plane by delta phi, it turns out there's a natural family of Riemann surfaces of genus 2, parameterized by this curve. I won't go into the details of that. This is what's called the Teichmuller curve story. But you can then take the Jacobians of these varieties, and you will get a curve in the three-dimensional moduli space of abelian varieties with principal polarization of dimension 2. But it turns out that the abelian varieties appearing here are special. The Jacobians have real multiplication, which I'll explain in a moment if you don't already know about it. And what that means is that this map to A2 factors through a map to the Hilbert modular surface associated to this arithmetic lattice, the one that we understand. So there is a two complex dimensional surface attached to SL2OK. There's a one-dimensional hyperbolic curve attached to delta 5, and the inclusion of delta 5 of infinite index into this group can be lifted to a holomorphic map from V into XK. That's already interesting, but what's truly remarkable is that this map, the image of this map is what's called a geodesic curve on this surface. That is, it is isometrically embedded from the hyperbolic metric on V to the Kobayashi metric on this Hilbert modular surface. And in fact, even this map to M2 is an isometric embedding. So this curve that's associated to billiards in the pentagon, it's already revealing some connection with complex geometry that's quite subtle. It is somehow extremal in the family of all curves on this Hilbert modular surface, and even among all curves in the moduli space of Riemann surfaces of genus 2. Okay, so I'm going to state a technical theorem now, which underlies the discussion so far. And it will have to do with these geodesic curves residing on these special surfaces. So the theorem is a little bit general. K can be an arbitrary real quadratic field. And to every such field, there's associated a Hilbert modular surface. And the theorem says that the cusps of every geodesic curve on this Hilbert modular surface coincide with P1 of the underlying field and satisfy quadratic height bounds. In other words, you can forget about the pentagon. All of the results I've discussed flow from the theory of curves on this Hilbert modular surface with this special property that they are what are called geodesic curves. Now, I didn't write this down, but it's already interesting that this says that if you have a geodesic curve on this Hilbert modular surface, it has to have some cusps, which means it can't be compact. There are no geodesic compact curves on Hilbert modular surfaces. Okay, now all the experts in the audience should be shaking their head. There's something called Shimura curves, which are well known and can be compact. And that's why every is in quote. If we exclude the so-called obvious or arithmetically based examples, then all the other examples are forced to have cusps and as many cusps as possible. And so the results on billiards and on this group delta 5 all flow from this theorem about curves on surfaces. Okay, now, I'd like to just give a hint of one of the ideas in the proof of this theorem. So the proof, in some sense, goes back to work of Leutbecker in the 1970s, and I reconsidered this several years ago and found a new kind of proof, and then I realized, going to a conference on arithmetic dynamics, that I was secretly using a height. And so I want to bring this height to the fore, and just since this is connected with some other topics in this conference. So let me talk about heights and I'm sure I'm using this word incorrectly. I'm going to use it anyway, descent. Okay, so what is the classical way you would try to prove that if you start with an element of Q adjoining root 5, that its golden fraction terminates? So what you would try to show is that as you apply the continued fraction algorithm, some property of the number you're looking at gets smaller. This property being some kind of a height. And if this height is bounded below, then eventually the algorithm has to terminate. So that's a sort of classical approach that's implicit in some papers from the 1970s. And what I want to describe is a more modern approach, which is, this is based on some discrete discussion, and this will be based on a continuous and more homogeneous discussion. And here the idea is to show that it has a geodesic gamma on this curve in the Hilbert modular surface. If this geodesic tends towards a cusp in P1 of k, then the height of the corresponding abelian variety, or rather the height of this point on P1 of k, as seen from the perspective of this abelian variety, tends to 0. So that's a lot of words, and I will unpack that in a moment. But the main point is that the classical approach is discrete, and you have to be very clever to figure out what h will work. Whereas this more modern approach, it's continuous, and the h is kind of natural. It falls from the sky via some simple considerations. Okay, so to say what this height is, let me remind you of a couple of things. And remember, I am new to heights. I think of myself primarily as an analyst. So I learned what the height is classically on Pn of k. So the height of a point given in homogeneous coordinates is obtained by taking the product over all places of the field, all valuations v, of the maximum of the coordinates, or rather the absolute values of the coordinates at those valuations. And this product is always greater than or equal to 1. Also, there's a basic theorem. The product of the valuations of a point in the field is equal to 1. That's the product formula for valuations. And that ensures that this height is independent of the choice of representative of the point on projective space. And as I mentioned, it's bounded below, which is critical for proving algorithms terminate. Now, suppose you don't really know about heights. There's something to do with primes in the field and how the multiplicities there. You don't want to think about all of that. There's a way you can get away with computing this height that only requires you know what integers are in your field, what the algebraic integers are. And it changes the height a little bit, but it's not too much and suffices for all applications. And the point is that it suffices to use the places at infinity and just take the product that you have here over the infinite places of your field, provided you only consider representatives of x where all the entries in homogeneous coordinates are algebraic integers. So this is an important nuance for me because it allows me to ignore the finite places in a manner that will be useful when we come to abelian varieties. Okay, so now let me say a word about real multiplication. So a polarized abelian variety means, with real multiplication, means the following. We have a polarized abelian variety. We have a totally real number field. The degree of this field over Q is the same as the complex dimension of our abelian variety. And we have chosen an action of K on the abelian variety A by endomorphisms. Well, since this is a field, and this is discrete, that's not quite what we want to do. So we take the endomorphism ring tensor Q, and then we want a map of the field K into this vector space, this rationalization of the endomorphism ring. And it should have the property that the elements of K, this reflects the fact that K is totally real, should be sent to self-adjoint endomorphisms of A with respect to the polarization. That's the definition of real multiplication. Now here's what I like about real multiplication. You start with an abelian variety of some high rank, and now you have this field K acting on the variety and therefore on its cohomology. And as a result, the first cohomology, say with rational coefficients, which can be quite large, it's like Q to the real dimension of the abelian variety, is simply a two-dimensional vector space over K with respect to the action of real multiplication. And so we can canonically associate to such a variety the space of K lines in H1 of XQ, in the rational cohomology of X, considered as a module over K. So there's a canonical projective line associated to every abelian variety with real multiplication. And also, K acts on the space of holomorphic 1 forms on A, and so we can choose an orthonormal basis of eigenforms for this action, and they're indexed by the places of the field, the infinite places of the field. Okay, finally, we can use all of this information to produce a height on P1 of K from an abelian variety with real multiplication plus the Hodge norm. And the definition of the height is the following. So you're given an element of P1 of K. Now remember, this was obtained by projectivizing the rational cohomology. So you can look, given a point in P1 of K, you can look at an integral cycle on A. This is an element of H1 with coefficients in Z that represents this point on the projective line. And then we can look at the period of each of these eigenforms over that particular cycle and take their product, and then for good measure, we normalize by 1 over G, where G is the dimension of the abelian variety. And this quantity behaves exactly like a traditional height on this projective line. And in fact, we can write it so it looks very much like the height we wrote down a moment ago. It's the inf over the integral points representing a given point on P1 of K of what I like to think of as the Hodge valuation of this particular class C. In fact, it is the Hodge norm of C considered as an element of the real homology of A. So what's nice about this is we have a way to take the Hodge theory on A and use it to build some valuations and then use them to build a height. And the fact I mentioned before that if you just concentrate on the infinite places of your field and only look at integral coordinates, that you don't really change the height very much, implies that this height is comparable to the classical height on this projective line, and in particular, it's bounded below in terms of the abelian variety. Okay, so enough of that. Let's just take a deep breath and finish the proof. So on a Hilbert modular surface, this height involves two terms. There's two eigenforms, and you integrate one over a cycle, and you integrate the other one over a cycle. The other one's sort of the Galois conjugate form, and that gives you a bound for the height up to a square. And the point is that when we're trying to show we have a cusp on our curve, we can choose a geodesic that forces this first term to go to 0 exponentially fast. Unfortunately, and what we'd like to do is force the height to 0. Unfortunately, it has to compete against this other term here. But it turns out the second term might go to infinity, but goes to infinity slower than the first term. And this is basically a simple Schwarz lemma argument. And as a consequence, the first term wins. The height goes to 0, but the height is uniformly bounded below in terms of A. So the underlying abelian variety must go to infinity. So your geodesic on the curve must go to infinity, which means your curve is not compact. And in fact, this geodesic has to go to a cusp. And that's a quick sketch of the mathematics behind all of these results. Okay. Now, Peter told me over lunch that he almost went into logic for his thesis, working with Paul Cohen. And we are quite close, potentially, to some logic theoretic issues here. So I want to draw your attention to this. Is there maybe some undecidability lurking in the background here? And just to give you the state of affairs, let me formulate a problem the way computer scientists do. So whenever they have a problem they want to consider the complexity of, they write it in capital letters. So my problem is called cusp of n. And this means there's a generalization of these groups, so they work for the regular n-gon, and this is, given a point in the field, explicitly decide if it is a cusp of delta n or not. And this is the same thing as saying if I'm given a slope, is it the slope of a periodic trajectory for the regular n-gon? And my question is it possible that for some value of n, say 7 already, that this question is undecidable. In other words, is it possible that there is no algorithm whatsoever to decide if a given point in K, a given slope is periodic or a given point is a cusp? Now, if you happen to have been given a cusp, you will eventually be able to prove that because you can enumerate all of the cusps in this group. But if it's not a cusp, how will you ever prove it's not a cusp? That's the whole question here. And there's very few methods known for proving a given point is not a cusp of one of these non-arithmetic groups. This is maybe a sharpening of the question that non-arithmetic groups are mysterious. So this is open already for the case n is 7. In this case, q adjoin root 5 gets replaced by a cubic field. It's q adjoin cosine 2 pi over 7. And for cubic fields, we have the whole discussion of Hilbert modular surfaces, but now there's one term that's winning and 2 terms that are fighting against it. And potentially, those 2 terms can team up and beat the first term. And in fact, it's not true in this group that every point that could be a cusp is. So that proof certainly cannot work. So let me just show you 2 experiments. Again, there's the analog of the inscribed star. So this is a slope. I'll call this a slope L of 1. Let me pretend this slope is 1. So this has a combinatorial length of 7. It hits every side of the heptagon exactly once. But I modified it just a little. And this is not an actual simulation. I got something of combinatorial length approximately 10 to the 40. So in fact, this is a periodic slope, but it's extremely long. And we don't know of any way to bound or predict the length of this periodic trajectory in terms of, for example, the height of the slope as described in terms of basic generators of the field. Okay. Great, so I wanted to, there's been so many new results announced at this talk, spectacular, one after the other. I thought I'd tell you something that's not known. Okay, I want to briefly look at a couple of other matters related to billiards. One question would be, Veach proved that if you have a trajectory that's not periodic, then it's uniformly distributed in your polygon. So you can ask, do long periodic trajectories become more and more evenly distributed in your polygon? And Davis and Liliev, who are experts on this type of question, who's looked at all the periodic trajectories, knew very well that this is not always true. So in fact, there's an infinite sequence of trajectories in the pentagon that leaves a hole in the middle of the picture. And this hole does not get smaller as the trajectory gets smaller. So you can ask, what are the invariant measures that can arise as limits of periodic trajectories? They speculated it might be a Cantor set, and the theorem is that in fact the limit measures form a countable set. It is a complicated structure. It's homeomorphic to the ordinal omega to the omega plus 1. And this describes the scarring behavior of billiards in pentagons. And it also completes the study of the closure of the ergodic measures for this billiard flow. So I don't want to say too much about this. I'll just hint that it has something to do with some non-abelian version of modular symbols for these curves attached to triangle groups. Okay, now the third question has to do with combinatorics of these billiard paths. So a very good question was asked at the beginning, where do I start my trajectory? And I like to start it at one of these edge midpoints. Now, you could say I'm just being capricious, but there's actually a canonical reason for this. Associated to this pentagon is a Riemann surface of genus 2, and the edge midpoints correspond to 5 of the 6 Weierstrass points on that surface of genus 2, which is, of course, hyperelliptic. So they're quite natural from the point of view of algebraic and complex geometry. And so when you're given a periodic slope, you can try all 5 different starting points and see what happens. So here, I've chosen the slope to be 0, and And you see if I start at this midpoint, I get an inscribed pentagon. Here I get an inscribed star. Here, if I start at this midpoint, well, the trajectory runs along an edge. It basically connects two vertices of the pentagon. And then I go back to star and back to pentagon. So there's a special trajectory which does not close, even though it started at an edge midpoint. It runs into a vertex in forward time and in backward times. I didn't tell you what to do with your billiard ball. When it runs into a vertex, it stops. It doesn't know what to do either. Okay, so let's do a different slope. So here's a different slope. And again, you see that there's a unique special trajectory that begins and ends at a vertex. In this case, it begins and ends at the same vertex. Here's another slope, and there's a special edge midpoint that begins and ends where this trajectory begins and ends at a vertex. Now we know what all the periodic slopes are. They're the points in P1 of Q adjoining the square root of 5. So there should be, ideally, a way to predict which edge midpoint is special just in terms of the slope. Without having to run simulations, without having to do continued fractions, it would be great if it were ideally just a simple arithmetic function of the initial slope. And so that's my problem, which is the special edge midpoint. And the answer is, there is a simple description of it. Namely, it turns out that these slopes are not just in P1 of K, they're in P1 of OK, the ring of integers for K. Now, K has class number 1, so it doesn't make much difference. But the point is that once you've represented a point in terms of a ratio of integers, you can then reduce mod 2. We can go down to this finite projective line, P1 of OK mod 2. By the way, OK mod 2, I mean, this is just Z adjoining the golden mean. And when you mod out by 2, you get the field with 4 elements. And so actually this P1 here just consists of 5 points. And guess what? The special trajectory corresponds to which of these 5 points your given slope represents when reduced mod 2. So beautiful and simple answer to this combinatorial question in the case of the pentagon. And in this case, I say the location of the vertex connection is what I call a congruence invariant, because it can be computed by reducing the slope to some finite projective line. That would be great if this were always the case. So I tried something in the regular 7-gon and the 9-gon. Things were working pretty well until I came to the 12-gon. And let me just show you a picture I generated for the 12-gon. Now, what I'm doing is I'm varying the slope. The slope is going to be t. T is just going to be an integer. And given the slope, there's a special edge midpoint. It's indexed by an integer k, which might be even or odd. So what I'm going to do is I'm going to use the parity of this special vertex, this special edge midpoint, to generate a walk on the line. Now, if the location of this special vertex were, in fact, a congruence invariant, this number k would be a periodic function of t. And you can see a very simple quasi-periodic graph when you drew this, say, for the first couple thousand values of t. But this is what you actually see. It looks very much like a random walk. And so I believe that, in fact, this very simple combinatorial question has essentially a chaotic answer for some values of n, and it's a congruence invariant for others. And it's very interesting and open problem to try to show that anything like this chaos is actually occurring. So for example, it's unknown if the ratio Wt over t tends to 0. I mean, the variance should be like the square root of t. You can see this only never gets bigger than about minus 40 or plus 40, even when t goes up to 2,000, but we don't know how to prove this ratio tends to 0. But we can prove that the location of the vertex is not a congruence invariant. It can't be predicted by a reduction to a finite projective line. So again, I want to kind of make short work of this with just a comment. We have a family of Riemann surfaces over this quotient by a triangle group V, there's some correspondence between the Weierstrass points and elements of the cohomology of this surface, or the points of order 2 on the Jacobian. And quite generally, there's natural maps from the fundamental group of the space into SL2 of OK mod L to the I. I was just doing SL2 of OK mod 2 a moment ago. Here L is a prime, of course. And these should be compared to the Galois representations associated to an elliptic curve over Q. Now, why do I say they should be compared? Well, in both cases, they're instances of monodromy on homology, if you think of the integral points on the torsion points on an elliptic curve as representing its cohomology. And there's a big theory that's been developed for studying these representations, proving the images are large. And a lot of this material can be transported, and it should be transported to this very natural setting of triangle groups. And maybe the more perspicacious way of describing the question here is the following. So we have a thin group, delta n. It's of infinite index in SL2OK. But what if we take the profinite completion of OK, the inverse limit of its quotient by its ideals, and take SL2 of this profinite group and look at the closure of our group inside of there. And interestingly, although this index is infinite, there's very general principles, well known to many of the experts here, that this closure is finite. And so a very natural question is, this question exists for every n, even n is equal to 5, the 2-5 infinity triangle group. What is this, I'll call it the adelic closure of this thin group of delta sub 5? And the answer is, ask Frank Caligari. So when Frank is not proving irrationality theorems, the first of their kind in hundreds of years, he's quickly knocking off problems that other people formulate, like myself. And he has a beautiful paper called The Congruence Completions of Triangle Groups, which gives a complete answer to this question. And in particular, Frank was able to amplify my result for NS12 and show we now know that the location of a vertex connection is a congruence invariant unless n is of a special form. For example, it has to be 0 mod 4 and not a power of 2. And the first integer with that property is 12. Okay, great. I have a little time left. So I'm going to discuss, I always call this a caveat when I'm speaking in English, and that's not what I mean. It's a complement. It's I want to turn to something that appears at first blush to have not a lot of relevance to what's been discussed so far, but it's of interest in its own right, and I'll try to tie it in before the end. So here's the complement. Forget everything you've heard so far. Wake up if you haven't been awake. So I want to discuss a spectral gap for triangles. Now, what do I mean by this? So I'm going to be interested, once again, in triangle groups, but this time in compact triangle groups. So famously, for example, if you can build a hyperbolic triangle where the interior angles are pi over 7, pi over 2, and pi over 3, generates a discrete reflection group sitting inside the hyperbolic plane. These numbers, 2, 3, 7, they want to live in hyperbolic geometry. 2, 3, 6 wants to live in Euclidean geometry. 2, 3, 5 wants to live in spherical geometry. It's associated to the icosahedron. So we can form a moduli space for all triangles where a triangle is simply described by giving 3 angles. And once we have these angles, the triangle may end up being spherical, Euclidean, or hyperbolic. The triangle knows from its angles which geometry it wants to live in. Okay, now, second element of the discussion. A triangle given by torsion points, i.e., where the angles are rational multiples of pi, or equivalently where it's associated to some roots of unity, it has a Galois orbit in this 3-dimensional moduli space. And so a given triangle has a bunch of Galois cousins, and we can ask, what is the chance that one of its cousins is spherical? Maybe the triangle we start with is hyperbolic, but maybe it has some spherical cousins. So I define the ramification density of a given triangle, specified by roots of unity, to be the number of triangles in its Galois orbit, which are spherical, divided by the total number of elements of its Galois orbit. So it's the chance that if you choose a triangle at random in its Galois orbit, that what you get is a spherical triangle. And the theorem is, this is the spectral gap, is that this ramification density cannot be arbitrary. It can be 0, it can be 1, but otherwise it lies in a proper subinterval of 0, 1. It's bounded away from 0 and it's bounded away from 1. And so if you think of the values that can arise for this ramification density as a kind of spectrum, then this shows that there's a spectral gap. And in fact, experimentally, the probably this interval is 1/12/4. But that would require an enormous amount of work, as far as I can tell, to rigorously prove. Okay, and by the way, there's a very simple argument that typically you would expect this density to be about 1/3. So maybe it's not so surprising that there's a gap. Also, the cases where the density is 0 or 1, they're pretty much understood modulo a finite set, which hasn't been computed, and I'll come to this in a second. So there's the proof. And let me just show you a fun part of the proof. So the moduli space of triangles is a torus, and if you have some triangles whose ramification density is, say, accumulating at 0, then you can show that these Galois orbits have to limit on a torus translate, that is a positive dimensional subtorus of this 3-dimensional moduli space translated by a torsion point. And so to prove this theorem in full detail, one needs to classify these special subtori, or their translates. And what they correspond to, we want to find subtori such that the torus never enters the space of spherical triangles. In other words, the triangles are, so to speak, purely hyperbolic on this torus. And this is a complicated but quite reasonable question in 3-dimensional Euclidean geometry. But I couldn't figure out how to explain this question and its answer because 3-dimensional Euclidean geometry is hard to convey on 2-dimensional paper. And then I finally realized there's a way to explain it in terms of a movie. And I can't put this movie in my paper, but I'll show it to you now. So here's the game I want you to play with me. So this is what I call the moving tablecloth. So it's a sort of a plaid tablecloth, and there you see these yellow rectangles which appear and disappear. That's the spherical region. And what we want to do is fire a particle at unit speed across this tablecloth and never touch the yellow. Now, you're allowed to touch the edge of the yellow, but you can't enter its interior. So how can you fire a particle through this moving pattern of obstacles so you never hit the yellow? So one way is like this. Okay, that was kind of obvious. The diagonal is never in the yellow, so that works. Does anybody want to suggest another way? A little louder? Ooh, you'll find that that's more or less what we're doing here. Okay, so let me show you a different one. You'll notice that there's these lines here that are slowly moving up, and they move up at a continuous speed. So if you're careful to stay on one of those lines, then you're always on the edge of the yellow, but you never enter it, okay? Well, that's another solution. Okay, and that's all, right? Yeah, that's what I thought too. So there's one more solution, which is a little bit subtle to find. And I believe that I proved that these are all of the solutions. And this is easily visualized, but hard to convey part of the analysis of this spectral gap. Okay, so let me just say a couple of consequences of this spectral gap. So you can use this theorem to prove a famous theorem of Takeuchi, which has many much better proofs, but it puts it in this general context. There are only finitely many arithmetic triangle groups. And because those correspond to groups where one triangle is hyperbolic and all of its Galois conjugates are spherical. So the ramification density is very close to 1. There's a lot of spherical conjugates. But there's an opposite kind of group, which I call totally hyperbolic. This is where the triangle is hyperbolic and all of its Galois conjugates are hyperbolic. And these groups have not been very much studied, but Waterman and McMullen proved many years ago that there's only finitely many totally hyperbolic triangle groups. And so here's an example of an arithmetic group. We mentioned this at the beginning, 2, 3, 7. These are its two Galois conjugates. These are both spherical triangles. So this has ramification. This is an arithmetic group because these conjugates are spherical, and it has ramification density 2/3 because 2 of the 3 places give spherical triangles. On the other hand, this guy, which I like very much, 1/14, 1/21, 1/42, has 6 Galois conjugates, and they are all hyperbolic. So this is what I call a totally hyperbolic triangle group, and its ramification density is 0. Okay, so just as a little overview, here is a list of all the co-compact arithmetic triangle groups. They've been known for a long time. There's 76 of them. And here are the 11 totally hyperbolic triangle groups. I've actually drawn tilings of the disk for each one, except that these are the 11 known totally hyperbolic groups. No one knows whether or not this list is complete or not. I mean, I would bet that it is, but this list was already found by Waterman and McMullen, and I believe that this list is complete, but that looks quite difficult to prove. So I want to make a comment here about wanting to build confidence in this assertion that this list is probably complete. And so I checked the following. By the way, 14, 21, 42 is going to play a major role in a moment. I wondered, are there any other examples? And experimentally, I checked the following. There's no other purely hyperbolic triangle groups with PQ and R less than 5,000. Now, 5,000 cubed is more than a billion. And then for each of these, you have to look at the Galois orbit, which might be roughly a billion in size. So it's, in principle, it's like a billion squared computation. It looks totally unfeasible. And then I learned something very interesting, which is while mathematicians have been sitting in their offices running Mathematica or maybe Sage on their workstations, the other scientists have been building enormous computer centers, in the case of Harvard, located on a river to supply, to supply natural renewable power for their enormous computing station and to cool all the processors, of which there are maybe 100,000, each of which has 12 cores. And they're doing protein folding. I mean, they're blowing us out of the water, and we don't even know how to log on to their machine. So I found out how to log on to that machine in Holyoke, Massachusetts, and in 30 minutes, I just grabbed 5,000 cores that no one was using, and in 30 minutes, I was able to verify this statement. So there's a lot that can be done. There's a lot of unused computing power sitting out there that if meek little mathematicians were to ask, they would be allowed to use. Okay, now, why is this a compliment? It's because it turns out that of these 11 groups I know, there's something very special about 14, 21, 42. I'll conclude with this. So the motivation is the following. First, I was talking about these geodesic curves. It's known that geodesic curves in moduli space of any genus have to have cusps. And we proved that geodesic curves in Hilbert modular surfaces have to have cusps. And in fact, most of these geodesic curves are related to real multiplication by a quadratic field. And so this theorem, in fact, implies this theorem in almost all cases. But one is left to wonder, what happens if we look at higher dimensional Hilbert modular varieties? And in brief, the theorem is there is a compact geodesic curve on a 6-dimensional Hilbert modular variety. It's not only is it compact, but it does not lie on any compact Shimura subvariety. So its compactness cannot be explained by by the usual arithmetic construction of Shimura subvarieties. Or to put it differently, the fundamental group of this geodesic curve is the Zariski dense in the fundamental group of the ambient Hilbert modular sixfold. Okay, so let me just say very briefly that this group is constructed using a result of Cohen and Wolfart, which allows us to take an embedding of this triangle group into the relevant arithmetic group and lift it to a geodesic curve. That requires some special things happening with quaternion algebras, which don't happen for the other 10 of the 11 totally hyperbolic groups. And but what we get at the end of the day is the following. We start with this 14, 21, 42 triangle. We pass to a subgroup of index 2. And then we take that group plus its 5 Galois conjugates. And we use the Riemann mapping theorem to construct a map from the disk, this quadrilateral, to these 5 other quadrilaterals. And we use the graph of that map to embed the corresponding curve into the corresponding Hilbert modular sixfold. And that gives the counterexample to the assertion that you should always have cusps for geodesic curves. It's the first counterexample I know, and it's the only counterexample I know. So this construction using 14, 21, 42 it appears to be the only way with modern technology to construct a curve of this type. And the reason is that what has to happen is this group has to, technically it has to, the corresponding invariant quaternion algebra has to split. That's required for it to embed in this Zariski dense way. And it's the only known triangle group with that property, and I believe it is the only such group. So there's lots of open problems here. I jumped from 2 to 6. I have no idea. I mean, I suspect I know what happens in dimension 3, 4, and 5. But what this really highlights is that we have very few constructions of totally geodesic curves on algebraic varieties. So I'll stop there. Thank you.
Thank you, Kurt, for a beautiful lecture. So any questions, comments?
Theorem of the movie. How do you prove it? I mean, what's it? Is it you said that those are the only things that avoid the yellow.
Right. So Peter's asking, how do you prove the theorem of the movie? So there's 2 points in that theorem. That theorem is not, the movie is not quite enough to prove the spectral gap. So there's 2 steps in proving the spectral gap. So the first is you have to figure out what these tori are that avoid the spherical triangles. And the way you do that is it turns out that the hyperbolic triangles form tetrahedra. So if you have a one-dimensional torus which avoids the spherical triangle, as you move along it, you get a string of tetrahedra. And you can just figure out what the possibilities are for how the strings of tetrahedra can fit together. So there's a combinatorial/geometric analysis, and this part is hard to visualize, but once you understand what's happening, say via these pictures, it's easy to prove. The second point is that you need to show that the Galois orbits of interest are eventually absorbed by these higher dimensional tori. And this uses the following equidistribution result, and it's special to roots of unity. It's not true for points of small height. It's that if you have the sequence of torsion points and their Galois orbits are getting denser and denser, they're accumulating on, say, Haar measure on a subtorus of positive dimension, then those points eventually lie on that subtorus. If they lay close to it, but we're not on it, then they would sort of spiral away from it. And so all but finitely many of them are absorbed by the higher dimensional tori. So once you've classified those, there's finitely many things left over. And I don't know how to enumerate the finitely many things that are left over.
More questions, comments?
So when you said you don't know how many of these groups, these totally hyperbolic groups there are, but you know there's finitely many.
Yes.
Is this one of these proofs that's effective in the number of them but ineffective in the height?
No. So the proof is what I just sketched to Peter. So if there were infinitely many, then they would be associated to one of these positive dimensional tori that I've already described. And so I rule those things out close to that, and then I know there's finitely many left over. I have no idea how many. I think I've written down all of them, but I don't know.
Also, for the 12 gone, since you were able to is this a case where, in fact, every rational point over that field is a cusp?
Yeah, so the question is, for the 12 gone, is every rational point over the field a cusp? So I have a confession to make, which is that theorem, that everything that could be a periodic slope actually is, that only works, it's if and only if the associated field is real quadratic. And that means it works for 5, 8, 10, and that's it. So for 12, the associated field is cubic, and we don't, sorry, for 12, I'm sorry, you're absolutely right. For 12, it's also quadratic, sorry, 5, 8, 10, and 12. Yeah, and that's why I was able to find all these periodic slopes. Yeah, that's right.
Questions? Actually, I have a basic question. So why do actually triangle groups appear in the study of billiards?
Oh, okay. So his question is, why do triangle groups appear in the study of billiards? Really good question. So in the study of an ideal of billiards in a pentagon, you can imagine that the group of cyclic rotations of order 5 appears. Yeah? But there's more. So what you can do is you take this pentagon and you put another copy of it below it, and then you glue together opposite sides. And you get a surface of genus 2. This is not opposite. Where does this go to? Here we go. Okay, so you glue these sides together and you get a surface of genus 2. And now what we do is we look for maps of this surface to itself which send straight lines to straight lines. Because billiard trajectories are straight lines, so that preserves the billiard dynamics. So we start with this polygon, which has very few symmetries. We build a Riemann surface together with a holomorphic 1 form, which it just records the notion of straight line here. And then we look for the group of real affine automorphisms, which is just another way of saying we look for the automorphisms of the resulting closed surface that preserve the notion of straight line. And this group naturally sits inside of SL2R, and that is our triangle group. So if we had done this with a square instead of a pentagon, then we would have just glued opposite sides. We would have built the square torus. And the square torus has a fairly small automorphism group as a complex manifold, but as the maps that preserve straight lines coincide with SL2Z, modulo the translation group. So this triangle group corresponds to the square, and the higher, more complex triangle groups correspond to the pentagon, polygons with more sides.
Right, but there are other subgroups of SL2R, so, but why is the actual triangle groups?
Yeah, that's right. So why are they actually triangle groups? So one could say that it's an accident of nature. This would be slightly misleading. The truth is that there's one new symmetry that's not obvious in this picture, but which I can draw for you. So when you build the surface of genus 2, this region here and this region here, they glue together. See, this edge glues here, this edge glues here. And inside of the surface, you then get something that's sort of like a cylinder. And now you can do a Dane twist in this cylinder. And it turns out that that Dane twist, together with the obvious point automorphism of order 5, already generate a triangle group. So it's in some sense an accident of the simplicity of the regular n-gons. And one reason I say that is, in fact, we know now lots of other billiards, some of them very exotic, which have the same kinds of properties. There's billiard tables which look like this, and we don't even know what these groups are. They're certainly not triangle groups. The whole story goes over, but there's a big question of what the groups are. They're again, non-arithmetic, non-congruence, all sorts of difficult and interesting questions are associated with them. But I swept that under the rug today to concentrate just on the polygons.